the chapter 11 homework. There were not a lot of problems here, but they're pretty lengthy. The first one, you were given this information, which is a velocity time graph, and that's the basis for everything else, parts A through I. You're also told that the particle we were talking about had a mass of 500 grams. So the first thing was to determine the acceleration time graph from that. So that's dv dt. Slope this graph is initially 10 meters per second squared, then negative 10 meters per second squared, then 0. So that's this graph. Here, we're trying to figure out the position time graph. So because we always have a positive velocity, we always have an increasing position. So it's concave up for the first 2 seconds, and after 2 seconds, the area of this graph would tell us where we are, which is at 20 meters. Adding in this area for this trapezoid from 2 to 3 seconds gives us the next part, and we're going to end up at 35 meters after 3 seconds, and then we'll end up at 45 meters after 4 seconds. This first part is concave up because we have an acceleration, a positive acceleration and increasing velocity. This part is concave down because we have a negative acceleration and decreasing velocity, and this part is a straight line, which is due to having no acceleration and a constant velocity. So here, you're asked to solve for the kinetic energy, and we basically plugged in the speeds or the velocities at 1, 2, 3, and 4 seconds for 1/2 mv squared. This is an exponential increase, exponential decay, straight value right there. For D, you're asked to have a force versus time graph. Well, using Newton's second law, force is equal to m times a, so 0.5 kilograms times this means that my graph here should have the same shape as the graph for A, but the values will be different. For E, the impulse is the area of this graph. So from 0 to 2 seconds, that's 10 Newton seconds of impulse. From 2 to 3 seconds, that's negative 5 Newton seconds to impulse. So for letter F, what we're looking to see is, does the impulse and the change of momentum agree with the velocities? So from 0 to 2 seconds, we have 10 Newton seconds of impulse divided by the mass would give me the change of velocity of 20 meters per second. So at 2 seconds, yeah, that's how fast we were going. For 0 to 4 seconds, we have only positive 5 Newton seconds. Oh, that's fantastic. 5 Newton seconds because we had a plus 10 and a minus 5. So that says that the velocity at the end of all 4 seconds would be only 10 meters per second. And that agrees with the graph also. 20 meters per second here, 10 meters per second there. For letter G, we're figuring out the work that's done. So, H, we're doing a force versus position graph. So here we know we have a plus 5 newtons of force that's acting for 2 seconds. And that basically goes through the first 20 meters. So that's combining this information with this information. During the next second, we have negative 5 newtons of force. Well, that's happening from 20 meters into 35 meters. So negative 5 newtons down here. H is looking at the work that's done. The work from 0 to 2 seconds is 5 newtons times 20 meters. That's plus 100 joules. The work from 2 to 4 seconds, which is really between 2 and 3, is negative 5 newtons multiplied by that change in position. And that's negative 75 joules. For letter I, we're looking to see whether or not these changes or this work done agrees with the change in kinetic energy and agrees with the speed. So from 0 seconds, we had 0 velocity. At 2 seconds, we had a change of kinetic energy, which is equal to the work of plus 100 joules. Well, that's going to go ahead and give us what we had thought. So the change in kinetic energy was plus 100 joules. That agrees with what we found earlier. Down here, At 2 seconds, we had this velocity and plus 100 joules. From 2 to 4 seconds, we have negative 75 joules of work. So at 4 seconds, we have a total of plus 25 joules of work done compared to when we started. So that means that would be how much kinetic energy we have at 4 seconds. That gives us 10 seconds, or 10 meters per second as a speed for 1/2 0.5 kilograms v squared. So at any rate, I think that this does a really nice job showing how momentum, force, work, position, acceleration, all those things agree with each other. There's a lot of different methods uh, in problem 41, but we're really looking at the same physics from many different perspectives. So in this particular case, for problem 42, for letter A here, it's asking how much work gravity does as thing is being accelerated upward at 1 meter per second squared for 10 meters. So if it's a 1,000 kilogram mass, gravity is pulling down on it with this much force, but you're moving upwards, so that FD cos theta, 9,800 times 10 times -1 is negative 98,000 joules. For B, asking how much work is done by the rope, well, tension minus Fg equals m times A, so the tension actually has to be 10,800 newtons multiplied by 10 meters, and that's in the direction of motion, so that's plus 108,000 joules. So the net work done is 10,000 joules. Thinking about that, that would equal the final kinetic energy. So that says that the object ends up with a speed of 4.47 meters per second. Looking at number 45, we're basically being asked to figure out the speed at the bottom of this ramp. If the person's up here, frictionless surface, but you have a 200 Newton wind force pushing horizontal. So essentially, what I would need to do first of all is figure out the length of the slope. That was 146.2 meters. There's a couple ways you could think about the work here. I chose that the initial energy was gravitational potential energy, and you lost joules due to the wind trying to slow the person down from what they would otherwise be doing, and that would equal the final energy, which is kinetic. So only the component of wind, which is parallel to the person's motion, would basically be acting against them. So I did 200 cos of 20 degrees, and that's 188 newtons. So at this particular point then, I've got the MGH was 36,750 newtons. The energy that's scrubbed off, if you will, by the wind is 27,500 approximately. So whatever I'm left with would equal the kinetic energy, and that gives me the speed of 15.7 meters per second. For 50, we've got a truck, object going up there. Initially, you've got spring potential energy, and then it goes into both gravitational and kinetic. So the spring energy is 22.5 joules. You end up with, just to go up that height, 19.6 joules being used for the 2 kilogram object. You're left with 2.9 joules of kinetic energy. And so you can use that to figure out how fast the object will be moving. But now, for part B, it says there's a sticky spot where someone spilled soda. Give you the coefficient of friction. So if we know this distance, we know the mass, we can find the normal force. So we're going to find out how much energy is scrubbed off using that friction. So that's 2.94 joules using force of friction, which is mu times mg, and then multiplied by the distance. So that's the negative work done on the object due to friction. So you only end up with 19.56 joules to get up the ramp, but you need 19.6 joules to do that. Pretty much within rounding, but it definitely won't make it, or it won't be moving at all once it gets to the top of the ramp. Last one's number 57. So in this case, we have someone up here, spring, no friction here, gets to the bottom, goes up a hill with a 0.15 coefficient of friction, and you want to find the distance it goes up the ramp. So big idea here for part A, we're asking like how fast the person's going right here. So that's a simple energy transformation from elastic to kinetic energy. But then here, to figure out how far we go up the ramp, we need to find out how much energy we have down here. And that's due to both the spring energy and the gravitational potential energy we have at the start. So when I look at that, that's 19,800 joules. So therefore, we're going to transfer that to heat, caused by friction and back up to gravitational potential energy. So the work done by friction is mu mg cos theta d. In other words, this particular distance per that angle, that distance up the incline is d, and the frictional force is this. So mg cos theta is the normal force, and the coefficient of friction multiply that gives us the frictional force. So for this then, this would basically be telling us the gravitational potential energy because mgh, but h is going to equal d sine of theta. So that h is basically the vertical part of that triangle. So in this case, I get 19,800 joules is equal to 617 d. So I get that d is about 32 meters up the hill. So a lot of stuff going on there, a lot to think about, especially in cases where mechanical energy isn't conserved. And remember, friction is a non-conservative force because it basically transfers into thermal energy when we have friction.